Welcome everybody to our September general meeting of the Fort Wayne Astronomical Society. I'm going to go ahead and start the meeting. We always usually wait a few minutes and we're going to jump right in. So one thing I wanted to talk about before we get rolling, and we had a really good star party with a couple new members added last Saturday, and it was a large crowd. I had to park way outside of our parking space, which was a nice problem to have. And also, I'm going to bring this up in case we had more members. There's going to be a booth at Science Central on October 2nd, I believe, 10 a.m. to 5 p.m. Wow, maybe that's my audio. The club is going to have a booth and a booth, table, chairs, electricity, and they want us to participate in their STEM program. No, that's Central. I think they're having a annual space day, and it would be nice if we can get some volunteers to help out. Just contact me, and we're going to have a good video and a new monitor. We have new TV. We'll be showing a good, they wanted us to show how different telescopes work. And Phil's made a really great show. So we'll do that. Maybe we can get together and do a few other things. So we do need volunteers and would like to have at least one solar telescope, the weather's permitting, outside the Science Central. October 9th, we're going to Girl Scout STEM 2021 at Camp Middleton in Huntertown. I'm reading my notes, as you can figure. It's a hands-on activity. It's going to be like 30 counties of Girl Scouts, K through 12. It is October 9th, 9:30 a.m. to 11:30. So we've got to get there a little bit early, I guess, to set up our stuff. Again, it'd be nice if we had a solar scope outside. They're going to have, so that's another thing to bring up. So our telescope update on that, the LX600, the 12-inch Meade in the observatory is, last I heard a few days ago, it was in California, the exporter. To send it back to the Mexican factory should be sometime this week, but that already hasn't made it. So I'll give an update at the board meeting. So those are some highlights. And any reports or anything? Anybody have any observing reports? Nope.
I saw lunar corona last night.
Wow.
Really cool. It was like at 3 a.m. and I got up because I thought my dog was gonna throw up, so I took him outside.
He helped you out.
Yeah, and I looked up and there it was, and I never saw it before, so it was cool.
Wow, that's it. Anybody else got something special?
Go ahead.
Yeah, I just was gonna reiterate what I showed earlier, where I had a let's see, I had printed up some like with the Club 3D printer. Here's a holder for the hand controller for the Orion ASIQ-5 mount, and it works. I don't need a web or anything like a belt to hold it on. So it's just held on by this clip and whatever. So, you know, just wanted to tell the club, here's a picture of the bracket, and here's a picture of the solar viewfinder that we've got. So anybody in the club that wants any of these items or anything else astronomical, it's a free. Okay, here's the solar viewfinder. It's a free print. Okay. Okay.
All right. Well,
Yeah, and the only thing I had was wrapped up my summer list of imaging targets, and yeah, had a good summer. Got the last two that I wanted.
Daniel, were you on the news the other night?
I was not.
You were not. Okay. Ed thought he saw, they were talking on one of the news stations about astronomy. He thought maybe that was you, but
Yeah, there was a teaser. I saw it last night about 7:15 or so, but it said tonight at 6 o'clock. It's either on 21.1 or 21.2. And somebody was there with a full get up operation thing, whatever like that. But I checked tonight and it must have been from last night's 6 o'clock because it wasn't on tonight.
Gotcha. Nope, was not me. Not this
I'll
time.
see, I'm gonna see if I can contact that young man and let him know that we've got some kindred spirits in town.
oh, you saw the deal, Gene?
Yeah, I've recorded it, so I've got his name. It escapes me at the moment, but
I might
I'm
already
sure
know
I
him,
can find
to be
him.
honest. I might already, I'm so involved in the astrophotography community online that, yeah, there's a good chance I know him already. Dude, what's his name?
All right. Well, is
What
there
was
any
his
more?
name?
Oh, sorry.
Oh, I was asking what his name was, because I'm checking my contacts.
Gene? Gene, do you have a name for the guy that was talking? You're muted, Gene.
Also,
I
does anyone
recorded
want to
that,
see the last
news
couple of images I
broadcast.
shot?
Wait a minute, Dan. Go ahead, Gene.
I recorded that news broadcast, so I've got his name from that. But I didn't write it down at the time, so I do have his name, but
Okay.
Not on you. No worries.
All right, Dan, go ahead. I'm sorry.
Yeah, no, it's fine. I'm waiting actually now. I'm rendering a new image in PixInsight, so it's taking a second. Okay, here, hold on. I'll show you guys the last few things. How do I share a screen? There you are. Sharing Safari. Share. All right, do you see my Safari?
Yes.
Oh, yeah.
So this is the tulip. I had a good time with that. It was fun.
Wow.
Yeah, it's in Cygnus, so it's, as you can actually see in the plot here, kind of where it is.
Mm-hmm.
So it's kind of halfway down the cross area. I had a lot of fun, a lot of nebulosity, so much nebulosity out there. I love it. I could spend a whole year in Cygnus. It's a beautiful area. You can't see through anything. Once you get like to these clusters, you see there's a ton of stars here, but I mean, that is just a solid wall of hydrogen that you cannot see through. So that was a lot of fun. This one kind of blew up online, my bubble.
Cool.
That one has been very well liked so far.
Wow.
And I shot that the day after I shot the tulip. So this one just sat on my hard drive for 2 weeks while I rendered the other data. So this one was cool. This one was a lot of fun, a lot of interesting processing techniques, because PixInsight's a never-ending mystery. And then the latest one that I did from the house, I shot Andromeda, which is always a classic, but I shot it at 910 millimeters, so a little different. But yeah, very, very punched into just one of the arms. So you can see individual star clusters over here and here in Andromeda. You can see the dust that's going over it. You can see even more star clusters and nebulas in Andromeda over here. Really, yeah, you can see all the dust lanes here. Let me turn off plate solving. Yeah, you can see all the dust lanes here. See all that. I had so much fun with this one. That one was fun. I got it at a good resolution too. So
What was your exposures and times?
this was 119 3-minute images. This was 42 10-minute images, and this was 32 10-minute images.
Wow, those are long images.
I normally do for nebulas like this. I do 10. That's just normally, but takes really good tracking to keep these stars as round as they are for 10 minutes. It's a lot of work to keep that tracking that entire time.
Yeah, you might have to give us a program sometime on your astrophotography.
It's fun. It's a good time.
Yeah.
I thought I had read in this email that you guys need help with PhD or guiding. I read something.
Yes. Daniel, this is Peter.
Hello.
Last Thursday, we, Ed and Joe's not here tonight, and Phil were out there, and we put the spectrograph on the 16, and we actually did a number of different stars. One of the issues we're having, though, is that as the star moves off the slit, it changes the intensity of the spectrum you're getting. And so Joe was saying that Daniel's going to have to come out here and help us on this as far as keeping that guiding just perfect.
Yeah.
Now,
as long as you have a guide scope or an off-axis guider and PhD, that's really it. You just need those two things and you're cooking.
can you use that off-axis guider or PhD, whatever you're talking about there? Can you use a small camera in a guide scope that's hooked into the computer to use that as a guider?
Yeah, that's what I would use.
Okay.
Yeah, purely that's what I'd be using.
Okay.
Yeah. If especially with that 16 and off-axis guider is going to be way too much work. Just maintaining that. I don't think anyone wants to do that. I don't. So my telescope's 910 millimeters, and using that with an off-axis guider is a pain too. So
then she's got to go left on.
Something to be aware of. But yeah, guiding is something that I've kind of, as you can see by how long these sub exposures are, I've 10-minute subs are not something they're how do I put it? I don't shy away from 10-minute subs, and I don't shy away from 20-minute subs. So guiding is something that I've worked on and I've got it down. So feel free to contact me with that stuff.
Yeah, maybe Joe's going to be gone for a couple of weeks. I'm going to be out of town for a few weeks. Maybe after that.
Be any issue. What do you guys image in? Sharp cap?
We've been using Sharp Cap with the spectrograph.
Yeah, it's a
not for stacking. Not for stacking, but just to view the spectrum.
Right. Yeah. No, I don't use it for anything else either. But yeah, I mean, Sharp Cap and PhD with a guide cam. I mean, that's it. Just another thing is, I mean, if you're going to be using, then again, the big 16 has a pretty big guide scope on it, so you're okay there. I was thinking if you need a big guide scope to guide properly with that thing, you need a huge one. That's why off-axis is recommended, but a ginormous pain.
Well, sometime we'll have to get you out there when we're hooked that up. It's going to be several weeks though, before we can get back on it again.
Yeah, just hit me up. I'll be around.
All right. Well, anything else before we call on Dan to introduce the program? Okay. I guess, Dan, you're on to introduce your program tonight.
There we go. Sorry. I held the space bar.
Do you like Daniel or Dan? I always...
it doesn't matter.
Well, whatever you prefer.
Yeah, no preference. I get called everything all day. But yeah, so we got Ben today describing and talking about really fun and exciting, literally exciting gamma ray stuff. Hopefully this should be very, very fun, because that stuff is, if in case you've ever dove into it, it kind of is mind-bending to think about how energetic it is and what it takes to produce it. And also he's going to be talking about stuff that he did at Ben, what was it, Veritas?
Veritas, yeah.
Yep. So, yeah, take it away.
All right. Thank you, Dan. All right. Share my screen here. All right. You guys see my screen? Okay.
Good.
Good.
Looks great.
Great. Okay, cool. All right. So just a brief outline of what I'm going to be talking about here. So first of all, what is gamma ray astronomy? How do we go about finding gamma rays from outer space? The motivations, what big science questions can we answer with gamma rays? I'd like to give a brief history of the field. I mean, there's of course a lot. We're talking about 50 years of history here, more than 50 years, but so just a brief history of that. I want to talk about the actual astronomy we can do with it. So kind of break it into two broad categories. So those within our galaxy, so those within the Milky Way, so supernova remnants, PWM, which that's pulsar wind nebulas, pulsars and microquasars, and then talk about the extragalactic sources, so sources outside of our galaxy. So mostly consist of supermassive black holes, but also a few starburst galaxies. I'll talk about Veritas. So that's the telescope I had the most experience on. And I'll talk about my own personal experiences with that, show some photos of out from Arizona. And then I'll just conclude by talking briefly about the future of gamma ray astronomy, so the future of the field. So hopefully it'll be a very bright one, no pun intended. So introduction. So by the way, I sort of apologize here. So I did kind of cobble this presentation in sort of short notice. So I'm reusing a lot of slides from my February talk. I don't think you guys will mind too much, but if a lot of these slides do look familiar to you, that's why I'm reusing quite a bit here. So I have 15 years of gamma ray astronomy experience. So I went to Purdue for both undergrad and for a PhD. And I did my PhD on Veritas. I spent 2007 on Arizona on the site. So I actually lived in Arizona for a year. And that was really great because that was a very exciting year to be out there, because that was the year where we celebrated our first flight and we got all 4 telescopes working together for the first time. It was a lot of hard work, but there was a lot of payoff. So finished my PhD in 2010. I should point out here, I have a physics background. I didn't come from an astronomy background, so I'm kind of learning the astronomy as I go. I'm still a lot about astronomy. I still don't know. I'll confess that. Yeah, my background is all in physics and so more of particle physics than astronomy. But my topic for my PhD was PULSARs, which is something I'll be talking a little bit later with the Veritas array. I liked working on Veritas so much, I continued on doing 2 postdocs on Veritas. One was the Argonne National Laboratory, which is outside Chicago. There I worked on the upgrade to Veritas, which I'll talk about later. And that's when I became involved in, as you guys know, I have quite the interest in dark matter. So that's when I started that involvement with the dark matter program. Then I became chair of the dark matter and astroparticle science working group in 2014. In early 2015, I left Chicago and moved to Montreal in Canada. And I was a research associate at McGill University. I did that for a few years. 2018, into that year, I stepped down and I left McGill and left Veritas and to pursue other career options. I took some time off. I spent, I'll just say 2019 was for my unemployed bum phase, although part-time I tutored in physics and math and astronomy. But mostly I just kind of took a sabbatical and took it easy. In February 2020, right before the pandemic started, that's when I decided to move to Fort Wayne and start with L3 Harris. So that could be really good or bad timing, depending on your point of view on that. But I think I joined FWAS in September last year. So I think we're looking at about a year of my membership in the club. All right, so let's get into it here. So first of all, just so everybody's on the same page here, what's a gamma ray? So a gamma ray is a form of light, and we see here the electromagnetic spectrum here. So going from radio at the low energy up through microwaves, infrared, optical light, which is what we see, and a lot of astronomy we do is in optical. Up through ultraviolet to X-rays and gamma rays. And so from the long wavelengths where it's low energy to shorter wavelengths where it's high energy. Gamma ray is just a kind of light, just like X-rays, just like visible light and radio and so on, but it's also the most energetic form of light. So, and we're talking, the range is huge, but we're talking about literally millions and billions times more energy than your visible light, than what we see, from our lights and from the Tycho Astronomy and at StarQuest. So the motivations for gamma ray astronomy, why do this at all? Well, first of all, we can do multi-wavelength and multi-messenger studies, so we can do basically the same sorts of things you would do with other types of astronomy. You get spectra and you get sky maps, and so you can do the same sorts of things you would do with traditional astronomy, just with an eye that can see at higher energies. So essentially you have an eye on the most powerful objects in the universe, because you need quite a bit of energy to create these gamma rays. The interesting thing we can do now is overlap with gravitational waves, the LIGO Virgo. That got quite a bit of headline news in the last couple of years, with them actually now able to see gravitational waves. So we can actually do follow-ups on these studies on black hole mergers and things like that. And neutrino telescopes, instruments like IceCube in Antarctica, which can see neutrinos coming from outer space, and we can have overlap with these types of interest as well. So not only can we overlap with other types of light, but we can interact with overlap with gravitational waves and neutrinos as well. So it's a very exciting time to be involved in this. And another interesting thing is we're learning that we can actually see further in the universe in gamma rays than we originally thought. We originally thought that there was sort of a limitation in how far out in the universe we can see in gamma rays. And it turns out that's not the case, that we can actually see much, much further. We thought that all the gamma ray sources would have a cutoff about redshift of 1 or so. And it turns out that's not the case. We can actually see further out than what we originally thought. Cosmic rays, high energy cosmic rays. Talked about this in my last 2 talks, actually. But what's the origin of high energy cosmic rays? We have potentially new physics that we can only learn at very extreme energy. So this is what I would call astroparticle physics. So essentially we're doing particle physics, but in a laboratory that's in space. I'm not going to talk about this so much in this talk. So maybe some other talk, I can come back and talk about that. You could do other types of astronomy. You can actually do optical astronomy with Veritas, stellar interferometry, which for interest of time, I don't think I'm going to go into that either. But I can go back some other time and talk about that. Last motivation is what is dark matter composed of, and I did a whole other talk about that for UPWS. For those of you who missed that talk or want to rewatch it, or you're streaming on YouTube or on Facebook, it's on YouTube, so you can go back and watch me give a whole other talk about dark matter. But I won't talk about dark matter so much in this talk. So what produces gamma rays in our space? So basically there's a few different ways where you can actually create gamma rays. First is a process called inverse Compton scattering. So essentially what happens there is you have a light or proton produced by some other process that gets upscattered, basically. So it absorbs energy from a high energy electron. So essentially it gets what we call upscattered to some other high energy proton. So it bumps into something else and becomes it was originally some other low energy form of light, and it gets upscattered into a gamma ray. They get produced in proton collisions. So you have protons collide at very high speeds, which will create other particles called pions, which will decay into gamma rays. This is processes like at the Large Hadron Collider in Switzerland will do this. Atomic particle decay. This is possibly, I talked about this also in my dark matter talk, but keep in mind that from what Einstein taught us, E equals mc squared, that with just a little bit of mass can become a lot of energy. So whatever the process is, you do need quite a bit of energy to create gamma rays. So Ed, in preparation for my talk, asked me to include something from Star Trek. I really couldn't find anything that was really appropriate here, so I'm doing Marvel Comics instead. I hope that's okay. How do we see gamma rays? Nearly all gamma rays get blocked by the upper atmosphere, and that's actually a good thing. I wouldn't have it any other way, because otherwise all the gamma rays would just kill all life as we know it on Earth. So it's a good thing that the atmosphere actually blocks these things. We can't use our eyes to see gamma rays because the gamma rays will pass right through us. So there's really only two ways to see them, and that's to either A, use satellites above the Earth, or B, to use telescopes on the ground that are designed to see, not see them directly, but see their effects when they hit the upper atmosphere. So there are satellites as well. I'm going to focus on the second one here. So the current generation gamma ray telescopes, there's basically three different types right now. The Fermi-LAT, so this is the satellite, this is space. So this is what we call high energy gamma ray astronomy. So this is about 10 MeV to 100 GeV. I'm not going to expect people to really remember these units, but just keep in mind that green light has an energy about 2 eV. So we're talking about millions to billions of times larger than visible light here. So satellites such as Fermi-LAT and Egret will see these essentially having these foils of tungsten that will produce, the gamma rays will collide into them and produce particles that Fermi-LAT will detect. The high energy, very high energy VHE astronomy, which will be the focus of my talk here. So these are ground-based imaging telescopes. Here's a picture of Veritas at sunset here. I'm going to be talking about Veritas because that's my personal experience, but other instruments, there's basically a big three right now. The HESS, MAGIC, and Veritas are the big three that are up and running at the moment, which are ground-based and air Cherenkov astronomy. Then if we want to go even higher energies than that, so above the very high energy, we go to the ultra high energy, which is about a TeV, so that's tera electron volts. So basically 1,000 times that, a GeV, which essentially you get big tanks of water, big water bladders up in a high mountain, and you can see the gamma rays pass through that, or the particles initiated by the gamma rays pass through those detectors. So these are ground-based, and these are water Cherenkov detectors. So I'll just talk briefly about Cherenkov radiation. So Cherenkov radiation is essentially the analogy that everybody uses, which is a good one, is that it's a sonic boom for light. So when an energetic particle travels faster than speed of light in a particular medium, it produces this cone of light here. So you have a particle that's traveling along at this very high speed, and it's giving off this essentially cone of light here. So you can think of that as like a sonic boom. So I should point out that it's whenever it's traveling faster than speed of light in a particular medium, and I'll just pause here and say that nothing can travel faster than speed of light in a vacuum. That's what that was kind of proved through relativity. So when I say faster than speed of light, I mean faster than speed of light when it's traveling through air or through water or some other substance. But this Cherenkov radiation, you can see that quite a bit in nuclear reactors. This image here is from a nuclear reactor, which you can see the blue glow here. And this blue glow from this nuclear reactor is actually the Cherenkov radiation. So you have very high energy particles coming off the nuclear reactor here, giving off this Cherenkov light. And so if you were to look at the spectrum of a Cherenkov light pulse, it's the light of it is in UV and blue, blue to UV, and it's just a flash of light that's just the briefest flash of light. It lasts only a few nanoseconds. So you have to essentially have a very fast detector, a very fast camera in order to detect Cherenkov light. So the technique for Cherenkov light is you have these, as I said, the atmosphere will block nearly all the gamma rays. So you have gamma rays that will interact with molecules in the upper atmosphere, and they will create a pair of electrons and positrons. So essentially you have this reaction going on where this gamma ray will collide and produce electron and positron. A positron is an anti-electron essentially. So you have a particle of matter and antimatter being created in the upper atmosphere. These in turn will interact, which will create more particles, which will create more gamma rays essentially. And you have this process here that those gamma rays will themselves interact, create more electrons and positrons. And then you just essentially have this shower of light and particles that just are created from a single gamma ray that will just, the process just keeps repeating itself until essentially the whole thing loses energy and just sort of peters out. Essentially you just have this shower of light that just dissipates. So you can get something from a single 1 TeV gamma ray, you can get something like 1,000 particles out of it. The same thing also happens with cosmic rays, and that's what this image is here. This is a proton simulation. So here we have a gamma ray simulation. So here's the simulation of the shower of light, and then here's the pool in a Cherenkov telescope. Same things will happen with our proton. And then here's the light pool created by the proton, and you can see it's kind of looks sort of similar, but more sort of spread out, kind of blotchier. That's a technical term, blotchier. But similar processes happen for cosmic rays, and this is a major source of background for these types of telescopes. So telescopes like Veritas use the Cherenkov radiation from these particles created by the gamma rays to essentially what we call reconstruct the gamma ray by taking the light from the air shower, and you get this pool light, and we can use that information to find out where in the sky and what sort of energy it has and so on. So move on to my next section here actually, before I do that, is there any questions up to this point? All right, I'll just move along here. So here's the sort of short version of the history of the field. The start, I would say, is 1953 when Cherenkov radiation was discovered, and it was named after a guy, Pavlov Cherenkov, in the former Soviet Union. And then a few years later, Morrison writes on gamma ray astronomy. So this is sort of the groundbreaking paper where it said, hey, we have this Cherenkov light that we've discovered. Why don't we possibly do astronomy with that? So based off that paper in the early 60s, there were some early experiments built in Crimea, Ireland, and the UK. And then in 1963, there was this paper Jelly and Porter suggested using the actual shapes of the images, which I talked about a few slides previously, to select the gamma rays from the cosmic ray background. 1967, so you had some Cherenkov images from space captured. That's this photograph here, this black and white photograph up here, where you have here these searchlights, and these are actually World War II surplus searchlights that were repurposed as essentially telescopes. This is on the future site in Veritas. Up here is the early experiments in the 60s, and this is what it looks like. Well, this is an older image, but this is what Veritas looks like a few years ago. And if you notice, both these mountain ranges on the top part and the bottom, these are the same mountains. So this is actually the same site. So on the future Veritas site, they were doing these sorts of experiments. In 1966, 1968, so they decided to construct the Whipple 10-meter telescope in Arizona on Mount Hopkins. And this was essentially a pretty fundamental telescope in this field. It's essentially the first real telescope that actually took worthwhile data in this field. Although it took a while for them to sort of get going, so from 1968 to 1976, so there were observations of many targets, but no actual detections of any VHE gamma rays. So in what's called the dark ages, after 1976 to 1982, for a few years there, entered what's essentially what we call the dark ages, where the Whipple 10-meter got shut down, which was pretty unfortunate. But good scientists don't give up. So in the early 80s, there was construction of an imaging camera. So essentially the camera was upgraded and replaced. So that was completed in 1984. So the Whipple 10-meter, this telescope, essentially the pioneering telescope in the field, got upgraded to 37 cameras, 37 pixels, up from a single phototube. And then later on in the 1980s, HEGRA, which was the first array of these telescopes, Whipple was only a single telescope. And so the first working array of telescopes was built in 1987 in the Canary Islands off Spain. And so in 1989, there was actual success. So there was actually the detection of the first TeV gamma ray source. That was the Crab Nebula. And so from 1989 to 1968, that's about 20 years. So you got to keep in mind that they were in the Arizona desert for 20 years looking for this. So that tells you quite a bit about, I find that to be a particularly inspiring story, that, you know, the perseverance of, you know, going out there and not finding anything, but, you know, you just sort of stick to your guns, you stick to it, and eventually they found something. So, yeah, I'm sure they had their detractors saying, "Oh, you're crazy for doing this," but they kept on. They proceeded undaunted. And then so this detection in 1989 was followed up in 1992 with the first source outside the galaxy. So that was the active galaxy Markarian 421. Veritas was first proposed in 96. The first collaboration meeting was in 2000 in Chicago, University of Chicago. Trevor Weeks, who I haven't really talked too much about that, but Trevor was essentially the pioneer of the Whipple 10-meter telescope. This was essentially his baby, his life's work basically was into that. So he was a really big pioneer in the field. Unfortunately, he passed away in 2014. But he was elected the first Veritas spokesperson. So he was essentially the leader of the field. HEGRA was dismantled in 2002. MAGIC begins construction on the same site. So MAGIC is another telescope I talked about previously. 2003, so there's a bit of a gap here. So Veritas wasn't actually, it was first proposed in 1996, but didn't actually get approved in 2003. So there was a bit of a gap there, but it was eventually approved. It was essentially, once Veritas got approved, we just had to get going right away. We had to build. We just had to go straight to construction. We had to just really get on the ball, because Hess and MAGIC also had first lights about the same time. So we were in this kind of race, so to speak, to try to get the detection, see what's out there. So we came along a little bit later. So Veritas' first flight was in 2007. Again, I was there. In 2012, both Hess and Veritas got major upgrades. The level time meter was decommissioned in 2013. And then in the late 2010s, CTA is being designed, and that's the next generation beyond Hess, Magic, and Veritas. That's the prototypes are being built as we speak. So, and some of them are being used. So to give you some idea, so gamma-ray astronomy in 2004, this is about the time I got started. My interest in this began. So this is the catalog. This is what we can see out there. So there's only about a dozen or so sources out there. And now going to 2020, this is a little bit out of date, but not by much. You can see that the sky is really populated now. There's a lot there more that we can see. So each of these dots is different gamma-ray, VHE gamma-ray source. So it was really exciting time to be part of this field, because we were just, it seems like every few weeks we're just finding something new and unexpected. This gives you the guide of all the different things you can see in gamma rays. So going from a dozen to 200 sources in just a handful of years was really great, really exciting time to be part of that. So I'll talk more about the individual targets themselves. So what the universe looks like in VHE gamma rays. Talk about a few individual sources here. So this is one, I picked this one out because I thought maybe some people in the club might be familiar with it. This is TYCHO'S supernova remnant. So this was originally discovered in 1572 by Tycho Brahe. So this is a supernova remnant. So essentially what's left after a supernova explosion. You have an image here in X-rays from Chandra. This is about, so this is about 449 years old. So from 1572 to now. And so this is 2 to 5 kiloparsecs, or 6,500 to 16,300 light years away. So quite a bit away, but within our own galaxy. So this is a supernova explosion that into essentially a clean environment. There's not much around it, so that's why it has essentially very nice sort of symmetrical look to it. And this is a supernova explosion that was essentially, or a supernova remnant, I should say, that's been pretty well studied at nearly all wavelengths. So this is the Veritas contributions to it. And then here we have the Fermi, so lower energy gamma rays contours here. So unfortunately, because Veritas doesn't have the greatest angular resolution compared to, say, a radio or a visible telescope, essentially from Veritas you get sort of this big blob here, but even with this kind of big red and yellow blob, you still learn something from that. So IC443, that's another supernova remnant, but it's a kind of a different one. So this is sort of a contrast here. So compared to the Tycho supernova remnant, this is a inhomogeneous environment. So the other one was kind of a clean environment, you got kind of this symmetrical look to it, whereas IC443 is kind of got this interesting shape to it. You got sort of this tail here, multiple regions to it. And that's essentially because you have varying belts of material. So it's not, it didn't explode into sort of a clean environment. There's lots of dust and gas in the surrounding space to it. So it didn't necessarily evolve into sort of like a sphere. It kind of became sort of lopsided, I guess, for lack of a better word. So, and the age of this one's uncertain, but interesting here. So this is what IC443, this blue cloud here, this is this is X-rays. And this has the Veritas contours, this map here superimposed in that. So you can see that they don't line up very well. And what we can learn from that is that this suggests that the emission is dominated by cosmic rays interacting with the sort of gas cloud here. So you have this sort of gas cloud here in X-rays, and this shock front that sort of evolves from it, and the gamma rays. So the dense clouds avoid are essentially Veritas is absorb, or I'm lost myself in thought here. So you have the infrared here that shows essentially the clouds, and you see that the Veritas emissions align with the cloud pretty well. But you have the X-rays here that sort of anti-correlate with that. So essentially you have the clouds here blocking the material from that's producing the X-rays. So talk about pulsars and pulsar nebula. So pulsars are a type of neutron star left from the stellar cores after the supernova. So essentially we're talking about more things that formed after supernova. A neutron star is essentially a very dense material, essentially gets squeezed so tightly that the protons and electrons making up the stellar core gets collapsed in each other. So imagine taking the entire mass of the Earth and squeezing it into an area the size of Fort Wayne. And that's what you're getting. That's essentially what sort of density you're talking about with a neutron star. And so pulsar being sort of a subtype of that, they spin very fast and with very high magnetic fields. So from this rapidly spinning, you kind of see here, this is in blue or purple here, we got this sort of torus, this kind of disk here. This is from the spinning neutron star here. You kind of have these jets coming off of it, and then you have the entire nebula surrounding here. That's the Hubble image here in the red and green. So the pulsar is essentially this engine that's accelerating particles that are part of the nebula left over from the supernova explosion. So the best known example, and this is the Crab Nebula here, Messier 1, is probably the best known example. And so this is essentially Crab Nebula, as far as I know, is the most studied object outside of our solar system. So first observed by Chinese astronomers in 1054 AD. And as I previously mentioned, this is the first TV gamma ray source that was ever discovered in the late 80s. It's also the strongest known gamma ray source. So it's essentially referred to as the standard candle of gamma ray astrophysics. As I said, there's a pulsar at the center of the crab. And so what we've seen from Veritas previously is the nebula around it, the surrounding nebula. But in recent years, we've been actually able to tune our analyses and actually find the pulsar as well. And that wasn't done until 2011, and I actually had a small hand in this discovery. So this is essentially the first pulsar seen at these high energies before. What you're seeing here is a graph here, a histogram of folding the gamma ray data along the pulse periods here. So, and it gets folded along two pulse periods here. So it's you'll notice that this side is identical to this side, and that's intentional. We plotted it this way on purpose so you can see essentially what's going on around zero phase here. But this is from 0 to 1 here is one phase of the pulsar. And you can see how it kind of peaks and drops, and there's kind of an interpulse here. This was kind of a shock to the community to actually find a pulsar at these energies, we expected that it would power the nebula, but it wouldn't. The pulsar itself would not actually produce these sorts of gamma rays. So the mechanisms here are not completely understood. So this is still worthy object of study, and I think the work here continues. So I'll talk about so next topic is microquasars. So this is a binary star system with a compact object. So a compact object being either a black hole or a neutron star. So you have a this is a artist's conception of a microquasar. So you can see it has this disk of material falling into the neutron star black hole here that's being fed by this other star. And then you have these sort of jets that shoot off of the object. So not everything gets absorbed by, say it's a black hole, not everything falls into a black hole. Some of it shoots off into these jets in the opposite directions there. So this example I'll use here is object LSI plus 61303, which is an 11th order magnitude star with a companion that's believed to be a black hole. So this is seen by Veritas, and the strength of the signal actually depends on how well or at what point in the orbit around each other that they so these two objects orbit each other about every month, give or take. I think the actual period's like 27 days or something like that. But it depending on the orbital phase here. So this is the signal, the amount of flux you get plotted with the orbital phase of the objects rotating around each other. So you can see that the peak of the signals, you only really see the signals at a particular part of the orbit. And so we think that the observations here in the bright part of the period can help constrain what the magnetic field of the part that where we actually see the emission region. So it can actually help constrain some of the physics of these objects. So I'm going to move outside of our galaxy now to extragalactic gamma ray sources. So the catalog for objects outside of our galaxy are mostly active galactic nuclei. So these are supermassive black holes at the center of other galaxies. And we're talking, when I say supermassive, I mean about 1 million to 10 billion times the mass of our own sun. So you think our sun is pretty massive, but there's objects in the universe that are much, much more massive than that. And as I've talked about with microquasars, not everything falls into a black hole, it gets eaten by the black hole. Some of it gets spewed into a jet at relativistic speeds away from the black hole. So it gets kind of scattered off the surface of the black hole and gets shot away from it, depending on how it falls in. Veritas is involved with many sort of multi-wavelength campaigns with other instruments. So here you see the Veritas spectrum is up here. It's a little bit cut off by zoom, but you have the spectrum of this particular AGN, PKS 1441, which, so you have the gamma rays up here, and then you have X-rays down here going down to, how far does this one go down to? This one goes down to X-rays, but we've been involved with work with radio telescopes and visible telescopes, so even down here. So we can see these types of objects across the entire electromagnetic spectrum, essentially. And by doing that, we can better understand the underlying physics of what's going on in these objects. And so another interesting thing about active galactic nuclei is there'll be flares seen in gamma rays where they'll get many, many times brighter, orders of magnitude flux higher than what their normally quiet state is. And the reasons for that are still not well understood either, but they'll essentially have these giant flares for essentially, they'll be really loud for really bright for a few minutes or a few hours, or sometimes even a few days, and even the period of how long it flares will vary quite a bit. And then they'll essentially go quiet again, and we're still not fully aware of how this happens or why. So a lot of the AGNs we see are blazars. So as I mentioned, there's this jet, and this is artist's conception of material falling into a black hole. Here you got a black hole in the center here, and you have this jet shooting off of it. So really what we're seeing is the relativist jet coming out of the AGN. And so there's essentially this whole zoo of different types of AGN out there. And most of the ones that we see, about 95% in gamma rays TV gamma rays are blazars. And blazars are a particular type where the jet just happens to be aimed towards the Earth. So the jet's being shot in our general direction. And recently, one of these blazars, this TKS 0506 in a flaring state, has been linked to observing high energy neutrinos, which I talked a little bit about earlier at the Ice Cube Observatory in Antarctica. So this is the here you have the Veritas sky map here, so in orange, and then these contours here are where we think the neutrino came from. And so the neutrino telescopes don't have exactly the best angular resolution, but we think the neutrino happens to be lying within around here. So, you know, there's a very high chance that this came from this particular flaring blazar. So if so, that'd be very interesting, linking those two things together. So, and then also outside of our galaxy, STARBURST galaxy MA2, I think some of you guys probably have images of this. So this is one of the very few STARBURST galaxies seen at these high energies. MA2, also known as Cigar Galaxy, is the only one that's seen by Veritas. Here's the Veritas sky map, and then here's the Hubble and Spitzer image. And this one's also of interest because there's also these objects have very high rates of star formation. So essentially they're stellar nurseries of lots of dust and clouds that's collecting together to form new stars. And this is also something that we believe to be cosmic ray accelerators. So we think that maybe some of the cosmic rays that we see on Earth are coming from these STARBURST galaxies. So I'm going to move on here to the introduction to Veritas, and then a little bit of life at the Veritas Observatory. So Veritas, that's the Very Energetic Radiation Imaging Telescope Array System. It consists of 4 telescopes in southern Arizona, located at Mount Hopkins in Tucson, so about 40 miles north of the Mexican border. So essentially, if you're traveling in Arizona, south of Tucson, but north of Mexico, you'll run into, just head due south, you'd run into Mount Hopkins and the telescopes there. The full array became operational in 2007 with a major upgrade in 2012. I already mentioned that. The field of view of these telescopes is about 3.5 degrees. The energy range is about 80 GeV to about 30 TeV with energy resolution about 20% or so. The angular resolution is about 0.1 degrees, and for a telescope of this type, that's actually pretty good. I know a lot of you guys are used to working on like arcsecond angular resolutions, but for a gamma ray telescope, this is 0.1 degrees is actually pretty decent. So the collaborations, collaboration photo, this is taken back in 2017 at the 10-year reunion of the first light. There I am. So the Veritas collaboration itself is consists of scientists in 5 different countries, the US, Canada, the UK, Germany, and Ireland. So there we are, staying in telescope 1 there. See our reflections there. Okay. The hardware of the telescope. So the cameras, the Veritas telescopes are essentially array of photomultiplier tubes, PMTs. Here's one of them looks up close here. It's about yay long or so. So you have this 10-meter mirror here, Tesla-elected mirror. So it's got 350 smaller mirrors that's composed of it. So you get the Cherenkov light from the gamma rays and reflecting off these mirrors into the gamma rays here. From there, they travel along the arms down the mount into these trailers, and then that's when the signals. These are analog signals, and they get digitized into trailers. And then there's a triggering scheme to figure out, as I said, that you have these the Cherenkov pulses are very brief, very bright, but very brief. So we have this pattern trigger to figure out, to discriminate what's possibly a gamma ray or a cosmic ray from what's normal background starlight, essentially. So a couple upgrades along the way. One I didn't really mention is that we moved one of the telescopes. We actually took apart one of the telescopes. So T1, the first telescope, used to be over here. And summer 2009, we took it apart and reassembled it over here. And that's to get a more optimal baseline between the telescopes. We realized that having T1 here and T4 here, they were too close together. So we disassembled it and moved it over here as part of that. That was kind of fun, actually. So that's a more optimal array configuration here, what's in this photo, which gave increased sensitivity to the whole array. In fall 2011, I was involved in the trigger upgrade. So to get better, faster discrimination on what's a Cherenkov light pulse and what's a background light pulse. So that led to better noise reduction. And then the big upgrade was in 2012, where we upgraded the entire cameras with higher efficiency, quantum efficiency phototubes. So essentially, we could collect more lights with the pixels, with the newer pixels. This also had the effect that we were able to lower the energy threshold. So here's some photographs of at the Veritas site. This is a little bit after dusk here. I don't recall who took this photo actually, but you see this is T1, I think, in the old position. So yeah, T1, T4 here. So it's we used to actually do the observing out of this trailer. We have a nice comfy observatory now, but back in the day we did observing out of this trailer here in the desert. Here's another nice one in Arizona. And if you've never been out there and you enjoy stargazing, of course, being on this call, I expect you would. It's really something. You should try to get out there while you can. Make it on everybody's bucket list, So on this particular image, so you have a nice image of the Milky Way here, and then you have nice images of Saturn and Mars, and shooting star here in the background. This is one of our telescopes. Dan or Julie, how are we doing on time?
It's 8:40. We got another 20 minutes till 9 o'clock. So
okay. Why don't we skip the YouTube videos, and then if there's time, I'll come back and watch those.
Okay.
Yep, I'm sitting here and listening and rendering.
All right, good. All right, so living out in Arizona, you get all sorts of crazy critters out here. You have tarantulas. You get tarantulas all around the telescopes. My office on the site used to have scorpions. And you just have to like scoop them up, like I don't know. I wouldn't squish them. I just take them outside and let them go. But you get tarantulas, scorpions, frogs. You actually get frogs out there during the monsoon season. They like it where it's damp, and this is a dehumidifier in one of our trailers, so it's leaking the water coming out from dehumidifiers, and the frogs really like that. So you get frogs around the trailers. Bats. This photo of bat was taken inside the observatory, got inside our offices, so we spent one night just running around chasing a bat. And that was my night, chasing a bat inside the office. How was your day at work? Well, I chased a bat. Geckos, lizards, all sorts of lizards. Bear. I took this photo of a bear. It was trying to get into the observatory. It was a baby bear. So it was kind of clawing. I think it was kind of curious, kind of clawing its way inside. And it was kind of cute, but it's like, oh, where's mama? Where's mom? So that was a little scary there. But eventually the bear, I think, got bored and kind of wandered off. Killer bees. So I took this photo of killer bees in Arizona. So this was back in September 2014. A swarm of killer bees decided to make one of the telescopes its home. So there's a monsoon season in Arizona, and we think that during the monsoon, it kind of disturbed the bees' home, and so the bees kind of up and left and decided to move into one of our telescopes. And you see this kind of mass, this kind of lump here on the bottom of the telescopes, and it's about yay big. It's probably hard, not easy to see the scale there, but it's kind of like yay big. And you'd think that was just them building the beehive, but no, that's just a solid mass of bees. That lump there is just solid bees. They're all like surrounding the queen or nesting there. But yeah, pretty much I got down to the observatory that day, and I looked at this. One of the technicians pulled me aside and pointed at it, and I believe the exact words on my mouth was, "I'm not getting paid enough for this." And then, of course, we pretty much had to quarantine this telescope. We just couldn't use it because we couldn't risk, the observers being stung to death, essentially. And of course, we had to sort of tell the hires up within the collaboration saying we have to shut down this telescope because there's killer bees inside. And so I sent off, got essentially the Veritas project scientist on the phone saying, and he pretty much was yelling at me like, "Stay the effing away from that telescope." This is a guy I hardly ever heard curse, but he said, "Stay away from that effing telescope." And it's like, yeah, I had no intention that wasn't going to happen. Because again, as I said before, I'm not getting paid enough for this. So these are just a couple of fun photos here. I showed this one in my dark matter talk, but I didn't really talk about it too much. This is essentially me. This is me during the upgrade with a crowbar here, and I'm threatening to smash the electronics here. Essentially, I was just kind of doing as a goof, as a gag, trolling one of my other colleagues who, so we were here to replace some of the electronics in this rack here. And I said, instead of ripping it out, I'm just going to smash it to bits. And, so just kind of messing with them, or trying to. This is a photo of me, much younger looking, a lot less gray hair, hiking with some of my colleagues out in the desert. They look much more prepared for it than I am. I came home, I was very tired that day. This isn't me in the forklift here, but I believe I was the one taking this photo, and this is us at night. And so what we do is essentially to align 350 mirrors, we'd have to take the snorkel lifts here, the forklifts, or cherry pickers, and move along and adjust all the mirrors by hand. So that's kind of nice grueling work for a graduate student to do. I have a few slides here talking about the future of VHE astronomy. These are our conceptions for CTA. I talked about this in my dark matter talk as well. So there's two potential CTA sites, two CTA sites. They're not potential anymore. CTA North, which is in the Canary Islands, pretty close to the Magic Site, and then CTA South, which is in the mountains in Chile. So CTA is the Cherenkov telescope array. So this is essentially the next generation of these instruments. So it's offering about order of magnitude greater sensitivity with expanded energy range and much smaller angular resolution. It's a global effort. So this is 31 countries with 216 different institutions. And as of summer 2019, probably update now, but about 1,500 different members of it. So just a huge international effort to get this going. So there's 2 different sites, as I discussed, and then 3 different types of telescope. So the Northern Hemisphere and La Palma, Spain. So this is the Canary Islands. I just read the other day that there's a volcano going off in the Canary Islands. So I hope everybody's doing well and hasn't infected things too much. But 4 large size telescopes. So Veritas is about, to give you an idea, the mirror is 10 meters in diameter. This is 23 meters in diameter. So this is essentially 4 times the size of the Veritas telescope. So 4 of those with 15 medium-sized telescopes, so about the same size as Veritas or Hess. And then Southern Hemisphere in Chile with 4 large-sized telescopes, 25 the medium-sized telescopes, and then the small-sized telescopes, which are about 4 meters in diameter, so much smaller than Veritas, but 70 of those. So this is just a huge effort to get this all together. And so there's various prototypes under discussion. LST, this is, a lot of these are artist conceptions, but I believe LST here is real. I think this has been built in La Palma. Various designs here. MST, that's in Berlin. I saw that one in person, actually. Not too familiar with a lot of these. SET, this is in Arizona. This is actually, as I mentioned before, we moved one of the telescopes. So we put the prototype, CTA prototype is in the old T1 position. So this is a novel new type of telescope, essentially, an alternative design for the medium-sized telescope. So sort of contrasting to the Veritas type design. Schwarzschild, I think I misspelled that, but Schwarzschild-Cousin design with 2 different mirrors. So essentially you have a mirror array down here, and then you have more mirrors here, and then this little box here in red, that's where the actual camera is. So you have light reflecting from the primary mirror to the secondary mirror to the third to the camera, which is actually here. Why do this? This is to provide a factor of 2 better angular resolution than what you get from the Veritas telescopes. So here's sort of the timeline. I'm not part of CTA anymore. I really didn't have a whole lot of involvement to begin with. But as I understand it, we're still in pre-production phase. The first prototypes are being built and data is being taken from now. So I don't know if COVID's really impacted the schedule too much, but I imagine next few years they'll move into sort of mass production phase where, and then sometime hopefully in the late 2020s, we'll get full array data from this new telescope. So I think that'd be really great. So just conclusions here. So through gamma astronomy, we have a window open to the highest energy objects in the known universe. There's a lot of open scientific questions still that they are exciting, at least in my humble opinion, they are. Hopefully, I convince you that you'll find them exciting too. But there's still a lot we don't know. And of course, that's what we do in science. We try to find out what we don't know, find answers to these types of questions. Veritas, as far as I know, is continuing operation to at least 2025. I think that's really good. The CTA prototypes are in the testing phase. Full operation, I guess, late 2020s, early 2030s. I'm not really sure. I think I can maybe reach out to my colleagues who are still part of CTA, and they probably know more than I do. Got links here to various websites. If anyone, I can send these out to anyone who wants to know more. So the Veritas website, the CTA website, the CTA prototype in Arizona has its own website. It's actually has a live stream as well, so you get live updates from if it's absorbing what's looking at. The catalog for BHE Astronomy is here. Used that quite a bit in putting together this talk, actually. I talked about this in the dark matter talk too, but you can actually hunt for muons with Veritas. So these are subatomic particles that Veritas observes, and you can actually do this at home through the Zooniverse project. It's a citizen science project where people can actually look at Veritas images and try to pick out these muon particles, and that helps us train AI algorithms to better pick them out, because humans are actually better at finding the images, but they're not as fast as the computers, of course. So this is a very easy and kind of fun way you can spend your spare time. If you're just on your laptop or tablet or what have you, on your phone, spend your spare time helping out Veritas astronomers. And yeah, I know I kind of went through a lot, threw a lot of people here. So if there's any of these topics that people would find particularly interesting and want to learn more about in detail, I could come back and give a future program on any of them. So that's pretty much all I got. Thank you all.
Any questions for Ben?
Thank you.
Yep.
Yeah,
Ben, thank you very much. I want to know, what did you do with the bees?
The bees left on their own, believe it or not. They kind of migrated after a few days. We think it was, and of course, I'm not any sort of bee expert. I kind of forced myself to be during that kind of scary few days where they were there. But what we think happened is the killer bees sort of, that was sort of a temporary home for them. And they kind of migrated on their own after a few days. And that was probably the best thing in the bees' interest, because if they were going to stick around much longer, we were going to call an exterminator. The bees showed up on a Friday afternoon, by the way, and none of the exterminators, the earliest the exterminators were going to show up by Monday, and by Monday they were gone. But yeah, so exterminators in Arizona are actually apparently pretty experienced in getting rid of killer beehives. So, but we were going to definitely leave that one up to professionals. But they kind of moved on. They kind of migrated on their own. They decided, well, we'll find somewhere else.
Hey, Ben,
Yeah.
how accurate are those mirrors? I mean, are those the same accuracy as like an optical telescope? Or, I mean, because they're awful big, you know?
Hey guys, real quick, don't want to interrupt, but my dinner just got delivered, so I'm going to bounce. Everyone have fun. Thanks, Ben, so much. This was awesome, fascinating. So,
Right.
but
Thanks.
you all have a good night. I'm gonna go eat.
All right, you too.
Good night.
Yeah. So, Jim, you asked about the mirrors.
Yes.
Yeah, so they are larger. So I don't think they're probably as accurate as what you'd find in an optical telescope. And I think that's part of the reason why we don't have the angular resolution as, say, a lot of other optical telescopes out there. Another thing to keep in mind is that they get exposed to, you can't keep them, the mirrors as nice as you could say, because they essentially get exposed to the Arizona heat and the winds, and they get the sort of harsh Arizona environment. So we go through and we recoat them every couple of years. So there's kind of a rotating program. We have a on-site recoating facility where we re-illuminize their aluminum mirrors, and we re-illuminize the mirrors, the glass, and we replace them. So they're probably not as accurate as I know for sure, but I don't think they're as accurate as what you find in an optical telescope. But we keep them pretty nice. We keep them, all things considered, being out there in the desert, we keep them pretty nice.
You said that you adjust them by hand.
Yeah.
Can't you get a computer to do that more accurately?
Well, no, and that's the new telescopes can. The CTA telescopes, that's a big part of it to get. Look at the new telescopes have adapted optics. So there's motors on each of the gimbals on the mirror mounts that will adjust, and of course they'll do a much better job than any human can. So actually, I guess the photo I showed of us adjusting my hand is a little bit outdated. Obviously this is more expensive to put motor mounts on each one of the mirrors. So I think at the time Veritas was being built, we didn't want to go through the extra expense of doing that when graduate student labor was cheap, and by comparison. But the newer telescopes can do this. The newer telescopes have these adapted optics where you can manually adjust the mirrors.
Money is always a factor.
Money is always a factor. That's true.
Ben, I have a question for you.
Yeah.
On the detector on there, you showed a photo multiplier tube.
Yeah.
As equal to an individual pixel.
Mm-hmm.
Is it the need for? Is the sensitivity so low on that Cherenkov radiation that you need? Like, why can't you use it like a regular camera chip or something?
Right. We need the higher gain that photomultiplier tubes can provide. You can't use a normal CCD because they just don't have the gain to amplify the Cherenkov signals.
So you need that additional amplification.
We need the additional amplification. Also, timing is a big difference. As I mentioned, the Cherenkov pulses are really short. They're only a few nanoseconds. And with a CCD camera, you just can't get that sort of timing resolution out of them. So you actually need photomultiplier tubes. So for Veritas and Hasset Magic, photomultipliers are the way to go. I think for CTA, they're looking into silicon photodiodes, which I think there's been, in the last 10 years or so, there've been a lot of advances with silicon photodiodes, and they're getting to the point now where they can meet the requirements.
Hey,
it seems
Ben.
like,
yeah.
Go ahead, Peter.
Seems like if you only had 500 pixels there, that you wouldn't have much detail of the signal.
Yeah, and again, that's another reason why you don't get the angular resolution that you'd want from compared to say an optical telescope.
Right.
But with I think with the next generation, if it's silicon photodiodes, I think that would be a substantial improvement.
Hey, Ben, you kind of threw me for a loop there. I always thought that you can't go faster than the speed of light, but you're saying in a medium you can actually.
In a medium, you can. So you can go faster than the speed of light in air, or Einstein said pretty much you can't go faster than the speed of light in a vacuum. So in space, in space or some other vacuum where there is nothing there, you can't exceed the speed of light with that. But what you can do is you can go faster speed. So when light will travel in air or water or any other substance that's opaque, light will actually travel slower than the speed of light in a medium. So what you can do is if you have a lot of energy, you can actually exceed the speed of light in a particular substance. But when Einstein and others say you can't go faster than speed of light, he's referring to speed light in a vacuum.
Okay, I guess I never listened to the last part.
It's a loophole. Think of it as a loophole, right?
All right. Well, never say never.
Never say never. Yep. That itself could be a future program I can give, because I actually did look for space itself being a medium and actually looking to see if we can go faster or slower.
Yeah, that's kind
of using gamma rays essentially to look for variations of Einstein, basically. I didn't find anything. I mean, Einstein's pretty robust, and he definitely came up with a lot of things that we're still learning to this day. But
yeah.
Hey, Ben, what was your living conditions like there, and your dining thing? Was it all catered? Do you have a French pastry chef? What was going on there?
Chili?
What budget do you think we had, Ed?
Well, I thought it was fully funded. I thought maybe you steak available 24.
Fully funded. Fully funded.
McDonald's?
No, actually, one of the technicians, Jackie, would actually cook for us once a week, and that was great. He was a really good cook, but he didn't that wasn't a job or anything. He was just kind of he liked doing that for the observers, and we were always really grateful for him doing that. And Jack, if you're having to listen through Facebook, thank you a lot. Let's see here. Actually, I lived in the first 6 months I lived out there. In Arizona, I lived in Green Valley, and keep in mind I was in my early to mid 20s at this point. But I lived out there for 6 months in Green Valley, which is actually a retirement community, because that was the closest community to the telescopes, and I wanted to live close to the telescopes. So the closest town was actually a retirement community. So I was like the only 20-something in a village of retirees.
So you're pretty good at pickleball and shuffleboard? Is that what you're doing?
My golf score improved. Green Valley actually has a lane for golf carts.
Well, thank you very much, Ben.
Yeah. So the 6 months out there, then after 6 months, I wanted to get away from Green Valley. It's a lovely place, but I'm in my 20s. So I moved into Tucson for the last 6 months I was there. And then when I was actually observing, that's where I personally live, but actually when I was observing, I stayed on the mountain. There's some dormitory up there. So that's that was really gorgeous. I should have put in photos of that because it's just really beautiful up there. But isolated, you essentially have to drive up this 17-kilometer trail that's one way. So you have to take radios with you, and you take the wrong step off this road, you're literally falling off the side of the mountain. There's not a whole lot of railing. And I was told early on, if you feel like you need railings to drive up this road, you should not be driving up this road.
Well,
Ben, a lot of the optical telescopes are going to remote observing.
Yeah.
Is that in the cards for this.
As I understand it, and I'm out of the loop because I've not been involved in Veritas in a couple of years now, but as I understand it, it's already gone to remote. And there was talk about it when I was leaving the collaboration, but I think COVID kind of forced people's hands because people didn't want to do as much air travel and travel to the site. So it kind of kicked the collaboration to high gear to get things automated. So it's my understanding, remote observing is a big part of the program now. And like, so there's, I think maybe 1 or 2 people on site now. And part of the problem too, and again, we were talking about money earlier, it was getting, in my experience in the 15 years of being a Veritas observer, it was getting harder and harder as time went on, as budgets kind of dwindled, to get the observatory fully staffed. So when I started, a full crew of 4 people were needed every night. And then as time went on and things got more and more automated and we got more and more comfortable with things, we went from 3 observers to, we went from 4 observers to 3 observers. Then when I left, it was maybe about 2 observers, and now a lot of it's remote. So.
Okay. Well, it's getting past the witching hour. Thank you very much for the program. Thank everybody for attending.
Very much enjoyed your program. Thank you.
Thank you. Thank you very much. Thank you very much.
Uh-oh, you got a
Yeah,
thumbs up.
I thought it was great and very technical, but very comprehensive.
Yeah.
Wow. All right. Well, I think I'm going to bail. And
all
right. Nice seeing we could have seen a few more faces, but I guess.
Hey, Julie.
Yeah.
Phil came late there. I was hoping he was going to share his photo of the man on the moon.
Phil, you're muted. You want to respond?
I forgot and got late, so I didn't get it ready, Ed. But,
Oh, darn.
Maybe the man on the moon's shy.
Maybe if you stick around, I'll
Well, I got the one you sent me. I just thought everybody else would enjoy it.
well, let me do some playing around.
Also, Phil, did you ever finish that Jupiter and Saturn shots?
Just Saturn.
How'd that come out?
It came out pretty good for what I expected. The Harnish Figure Crow, that red telescope, does have a lurch, and so but it's able to photograph the planets pretty good. Let me see if I can. I have a GIF made up that is it's kind of made up of just 4 frames. Let's see if I can that doesn't work there, so I gotta open it like this. Now I gotta get back to my Zoom. I'm not sure if I can do that.
Bill, if I could have found my mute button, I would have given you a phone call and let you know you're missing the meeting.
Yeah, well, I would have taken it, but I got a good dose of it, so I liked it. Yeah, it was cool. I don't know. I can't get back to my Zoom in a way, I guess, to see my screen share.
Okay.
I don't think.
I was kind of hoping, Julie, that new couple that came out the other night to the observatory would join the meeting today. I guess they didn't. Did you get that data on them, Phil?
On what? The
new couple that joined, they claim they joined through the website on their way out there.
We got 2 names on there, and I think it's one of them, but I can't remember. Was his name Adam?
I can't remember his name either.
But I did get, we're up to date as far as, we got 2 new members since our Friday or Saturday night thing. So that's nice. Okay, maybe I'm getting there. This is the planet one. It's an animated GIF. And you can see it's at prime focus. There's no magnification at all. So it's prime focus. The first, this is the long exposure, then combined files, and then the moons.
It's actually pretty cool.
There's the overexposure. So I did learn that even in that overexposed, that if you mess with the gamma, there was some detail in there that I used, even overexposed, where you think that that's cropped out, there was definitely data there. So yeah, this is just an animated GIF.
Okay.
And 15 seconds. And the I think the short exposure, the first one right there, yeah, was 1/4 second. So anyway, that was Saturn. It's kind of what I wanted to see. I just wanted to see if I could see all the moons.
Right. Pretty clever.
All right. Well, good night, all.
Okay.
Really?
Well,
Bye.
Okay.